Well, let's take a look at this exam. Now, this is a rather unusual exam. This is the Differential Equations exam from spring 2023. You might say, well, what makes this so unusual? Well, it turns out there was an ice storm the day that this exam was supposed to happen, and the exam was canceled. So nobody took it. So it's, we could say, look, nobody lost a single point on the exam. Best performance of all time. Well, that's at least one way to look at it. But you know, it feels a shame that nobody gets to do the exam. So let's do it together. And so we're going to go through and do our exam. There's 6 problems, so we'll get to do 6 problems. And note that this semester we've added a new instruction, and it may or may not play a role in things to come. But just note, our final answer should not involve complex numbers, which isn't to say we can't have complex numbers show up in our method of solution. It's just at the end, there's no complex numbers. All right, well, we should start this by writing down that this is going to be our answers, and then we'll be ready to go. Number 1, find in implicit form the solution of the following initial value problem. And then we have x e to the y plus x squared plus 2y, all of that times y prime, plus e to the y plus 2xy equals 0. And this has to pass to the point 1 comma 0, that is y equals 0 when x equals 1. Now there's a couple of things that tell us what kind of problem this is, or at least we should say there's some hints. Now one hint is this word implicit. Usually when we see implicit, that's a good clue that it's going to be one of 2 things, namely either separable or exact, and usually biased towards exact. But then the other thing is when we look at the sort of the format of the problem that's been given to us. So something times y prime plus something equals 0. Classic. This is the way that we would write a problem that's exact. So I say, all right, good. We've got an exact problem. We put on our exact hats and we begin. So the first thing is, let's rewrite this y prime. We'll think of it as y prime is dy over dx, and then we'll multiply through by dx, so that this is the same as saying, let's solve x e to the y plus x squared plus 2y dy plus e to the y plus 2xy dx equals 0. All right, so we've rewritten in this way. And now, why are we doing this? Well, in the back of our minds, we say, hey, you know, we're really after a special function. And in this special function, this part right here, this is our f sub y. And this part right here is our f sub x. Now, this would be true if it is exact. We don't know it is, but we suspect. And our answer that we're going to have at the end is going to have the form f equals a constant. Okay, so that's what we're building to, is what's this function f where we have these partial derivatives? Once we know the answer, life will be good. And so we say, okay, well, let's integrate, right? Because what do we have? We have the derivatives, and if you have derivatives and you want function, you integrate. It's, you know, it's one of the things we learned to do in Calc 1. Okay, so we're going to integrate this part with respect to y, and we know it's with respect to y because of the dy. Similarly, we're going to integrate this part with respect to x. We know it's with respect to x because of the dx. So we have integral of x e to the y plus x squared plus 2y dy. And when you integrate with respect to y, you treat x like a constant. So a constant times e to the y, integral of that is x e to the y. A constant, well, that would be the constant times y. And 2y would be y squared. And then anything which didn't depend on y, call it c of x. Okay, next part, we integrate this other part with respect to x. E to the y plus 2xy dx. So e to the y is no x, so it's like a constant. So the integral of that, well, it'll be x times our constant. Here, 2x, integral of that is x squared, and y acts like a constant. So we have x squared y, And then we have plus something, which depends only on y. All right, now at this point, we should be careful and justify that what we're doing actually works. In other words, do we have something that's exact, or do we have something that only we're mimicking exact? Because if something's not exact, our process breaks down. And here's the check, and you should always check. It's a good thing to check. You look at these two pieces, you say, look at the parts, and when I talk about a part, it's something separated by plus or minus. Look at the parts that involve both x and y, and we say, aha, these agree. Now, that says that where they should agree, the parts that involve both x and y, they do agree. Now, parts that only involve y or only involve x, they don't have to agree. But now we know that these agree, so we can say, so this is in fact exact. All right, so that justifies that what we're doing is actually valid. And it's nice to know that you're doing something which is valid. Okay, well, at this point, we're pretty close to having our f. We do is we take the part where they agree, x e to the y plus x squared y, and then the parts which only involve y and only involve x. Well, in this case, there's only involved y term. There's nothing that only involves x, and that's okay that that's true. And that equals our constant. And working our way through the alphabet, we use e. So that's what all our solutions look like. And so, if our question had stopped there, if that had been our question, we'd be done. But of course, there's some initial conditions. So we got to do the initial conditions as well. So what we're going to do is we're going to plug in x equals 1 and y equals 0. So 1 e to the 0, 1. 1 squared times 0 is 0. 0 squared is 0 equals e. So that tells us what we know e. We know e is 1. And so we put that in. We get x e to the y plus x squared y plus y squared equals 1. And we're done. We're done. Life is good. What a fun problem. A nice way to start an exam. You always want to have one that just feels like it flows. And this is one of those. It's a nice, it flows. The only thing that you need to know is what kind of problem it is. And once you know, you just follow the process. All right, well, let's keep going. Number 2. Find the solution to the initial value problem, xy prime minus 3y equals 2x to the 5th with y of 1 equals 6. All right, well, what kind of problem are we dealing with here? Well, if you look, there's only two places where you see a y. And you see a y prime and you see a y. That tells us that this is a linear first order. So we're going to use the linear first order technique, which you can also say is integrating factors. Okay, so this is an integrating factors problem. All right, so what are we going to do? Well, we first off put it in the right form. Now, what is the right form? You want to get the y prime term with the 1. You want to make sure the y term is on the same side. So for us, we would say, well, it's not a 1 yet, it's an x, divided through by x. So we would say y prime minus 3 over x y is equal to 2x to the 4th. Okay. Now, from here, what we're going to do is we're going to grab the term in front of the y. So this minus 3 over x, that part is going to help us find our integrating factor. And in particular, what we do is we're going to find e to the integral of minus 3 over x. Well, if you do these problems a lot, you'll see that there's a very common thing which happens. And that is that we're going to have integrals with a 1 over x involved. Now, what does that really mean? We're going to get used to seeing logs. So we've got to make sure we know our logs. So this is e to the minus 3 natural log x. We don't need to worry about plus c when we're doing this. Or if you like, that's e to the natural log x to the minus 3. E and natural log are inverse functions, so this will become x to the minus 3, or 1 over x cubed. Great. Now, what is this? Well, this is what we call rho of x, and that's our magic integrating factor. Okay, so, all right, how does that work? Well, the key is now you multiply everything by rho of x. And when I mean everything, this equation, once we've gone the 1 in front of the y prime. So we get that 1 over x cubed y prime, and here minus 3 over x to the 4th y is equal to 2x. Now, you might say, well, what has that done? But here's the thing. We always, always, always know the magic. The magic is this left-hand side, guaranteed 100% of the time, it's going to be the derivative of your rho, 1 over x cubed, times y. It has to be. If it's not, mistakes were made. And I say, okay, so what does that mean? Well, it means it's really super easy to integrate that. And we like things which are super easy to integrate. In fact, it's our favorite type of integral to do, the super easy kind. And so we're going to integrate both sides. And once we do that, what do we get? Well, we get the following, namely 1 over x cubed times y is equal to x squared. And then now you do need a constant, plus c. Or we can say y, multiply everything by x cubed, is x to the 5th plus c x cubed. Now, if we were looking for general form, we'd be done. But we're not. We have some initial conditions. So we need to put our initial conditions in. All right, so y of 1 equals 6. That tells us what? Well, it tells us that 6 needs to equal 1 to the 5th plus c times 1 cubed, which is 1 plus c. Or we could say that that says c has to equal 5. So our final answer is y equals x to the 5th plus 5x cubed. And we're done. Ah, fun problem. And this is another one where once you know the technique, there's a very nice set procedure, and you just follow it, and life is good. So, all right, good. 2 down. We're making great progress. Let's keep going. Number 3. Write the general solution of the differential equation, the 5th derivative of y, and that's what this notation means. So that means not y to the 5th power, but 5 derivatives of y, minus 4 times the 4th derivative of y plus 5 times the 3rd derivative of y equals 0. So this is one of our favorite kinds of differential equations. Constant coefficient, linear, homogeneous. And so we have a procedure. And so roughly speaking, what our procedure is we have a differential equation, and we're going to turn it into an algebra problem, and in particular, really a problem which involves finding roots. So we're going to find our roots. And then once we have our roots, we get up into our ODE solutions. So that's our procedure that we follow. Okay, so let's start by saying, what's our algebra problem? Well, in our case, thinking of our solutions of the form y equals e to the rx, and so that's where this step comes from, which we know, but we'll just go ahead and make a note there. We say, okay, this really transforms this into the polynomial r to the 5th minus 4r to the 4th plus 5r cubed equals 0. Now, we have our algebra problem. So we need to find the roots. If you want, we're trying to get to the root of the problem. It sounds like a very productive thing to do. We see we can factor out some r's, so we'll do that. So we have r cubed times r squared minus 4r plus 5 equals 0. Now, r cubed, that's nice. That says that we have roots of 0, 0, and 0. In fact, we have 0 3 times. A triple root. R squared minus 4r plus 5. We attempt to factor it. Okay, we didn't succeed. Okay, well, when we don't succeed in factoring, we don't panic. And we just say, all right, quadratic formula. Okay, so we have that our roots are negative b, which is 4, plus minus the square root, b squared, 16, minus 4ac, minus 20, all over 2a, 2. Well, 4 over 2 is 2. Now, 16 minus 20 is negative 4. And when you see a negative, you're like, how are we going to do it? Oh, yeah, square root of a negative is I. And of course, square root of 4 is 2. There's a 2 downstairs, so we get 2 plus minus I. All right, so we have 5 roots, 0, 0, 0, 2 plus minus I. Now, there's a pro tip here, which, of course, we remember from back when we did algebra. The number of roots has to match the degree of the polynomial. So if you have a 5th degree and you have 3 roots, that means you haven't found 2 roots yet. Or if you have a 5th degree and you have 8 roots, oops, hold on, mistakes were made. Step back and check your work and say, wait, hold on, some of these roots don't belong. There's some imposters hiding here. All right, so now we've worked through where we have the roots. Well, what comes after the roots? So the next step is we need to translate this into solutions. All right, so what happens? Now, let's talk about the zeros. Those are repeated roots. So normally, we'd think of it as e to the 0x. So the first 0, that would be a 1. Now the second 0, we would think, oh, 1 again, but wait, we already have 1. We need something new. Every root should give us something new. So what's the new? Well, in that case, you do what I like to call a bump. And so it won't just be 1, it'll be x. And in the next one, similarly, you get a bump again, x squared. Okay, so those are going to be 3 pieces. The 2 plus minus I. Now remember, we kind of noted at the beginning, complex numbers may show up in our solving, but not at the end. So we need to translate this into things which don't involve complex numbers. And the punchline is, when we see complex numbers showing up, it leads to sines and cosines. And so we say, okay, great. What we have is that the real part, it's still the exponential part. So that's e to the 2x. But now, the imaginary part is going inside the cosine and the sine. So e to the 2x cosine x, e to the 2x sine of x. So the 2 goes inside the exponential. The 1 goes inside the cosine and the sine. All right, good. So now we have our 5 pieces. And so we're almost there. We need to write the general solution. What we really have is 5 different functions, which are each solutions, but we can have the principle of superposition, which means that we can stack the solutions one on top of each other. And so we get our answer, well, some constant times the first solution, some constant times the second, some constant times the third, some constant times the fourth, and some constant times the fifth. Now you might say, is there a particular order you need to write these in? And the answer is no. You just have to make sure that you get them all. And there we go. And this is good. We started with the 5th degree differential equation, so we should have 5 constants at the end. We do. That's a great sign. We're on the right track. Life is good. Life is wonderful. All right. Well, we're halfway done. And it just feels like we're getting started. Well, okay. Let's keep going. Number 4. A group of fish has 2 things affecting its population, which is denoted as a function p of t. The first is internal growth, which follows the logistic model, k times p times m minus p. And the second is external fishing, which reduces its population by a fixed amount, that's h, every year. So we have that the change in population is the combination of the internal and the external. And of course, because it's reducing, we subtract h. All right. Now, we have some information. For these particular fish, we have h equals 4. When p equals 2, p prime equals 3. And when p equals 3, p prime equals 5. So we have to determine k and m and rewrite, but do not solve. Some of the most favored words on a math exam. Do not solve. This is about setting it up. All right, set up the differential equation using the values for h, k, and m, and we know what h is. All right, so that's good. That's good. So what do we need to be doing here? Well, we take a look and say we really need k and m, right? And so that's where this information should probably come into play. And so notice it says p prime and p, and we have our formula. So we can update. We say, look, well, p prime is equal to k times p times m minus p minus 4, right? Because we have a 4 there. And say, all right, well, let's plug things in. So we're going to plug in p equals 2 and p prime equals 3. So we're going to get that 3 is equal to k, and then times 2 times m minus 2 and minus 4. And now we'll do the same thing over here. P prime 5 is equal to k times 3 times m minus 3 minus 4. Well, if you look at this, we could rewrite this as saying, hey, 2 times k times m minus 2 is equal to 7, right? Because I just add 4. And 3 times k times m minus 3 is equal to 9. Because again, I can add. Now the goal here is to eliminate a variable. There's lots of ways to go about doing it. And this one is a little bit more subtle because it's not a linear equation. But of course, just because it's more subtle doesn't mean we can't do things. There's lots of ways to proceed. And I'm just going to say, hey, you know what? Let's just divide. Right? Why? Well, because that will eliminate a k. Really, your goal is when you have two equations, two unknowns, how can I get that to one equation, one unknown? Because that sounds a lot easier. Because it is. So, okay, if we divide, we can say, oh, that really says 2 times m minus 2 over 3 times m minus 3 is equal to 7 over 9. Well, cross multiply. 18 times m minus 2 is 21 times m minus 3, or 18m minus 36 is equal to 21m minus 63. And okay, we do some rearranging. For example, we can subtract 18m and we'll have a 3m. We can add 63, and of course this one you have to think about for a second. What's 63 subtract 36? And the answer is 27. All right, so lo and behold, we get m equals 9. All right, so that's m. How do we get k? Well, once we know m, we can plug it in to either equation, doesn't matter. So we'll get 2 times k times 9 minus 2 is 7 equals 7. Well, the 7's divide. 2k equals 1. K equals a half. Okay, we found m and k. All right, so that was part of our problem, so we should box that. So this says determine those values. And then it says rewrite using those values. All right, so we have that p prime is equal to 1/2 times p times 9 minus p, whoops, and minus 4. And there we go. There we go. Well, that's only half the problem, right? There's a part B. Okay, so let's move this up a little bit. And it says, for the differential equation from part A, this one we just found, draw the phase diagram and classify all critical points. Okay, well, actually, before we draw the phase diagram, let's do the find the critical points part of this. So we're going to set p prime equal to 0. 0 is equal to 1/2 times p times 9 minus p minus 4. I'm going to multiply through by 2 and also distribute the p. So I'm doing 2 steps at once, which is always dangerous for me. But you know, sometimes I like to live dangerously. And all right, so we get to this. All right, I'm going to multiply through by a minus and rearrange the first two terms. And so we get 0 is equal to p squared minus 9p plus 8. All right, good. Well, now what happens? Well, we hope, fingers crossed, that it factors. And, well, of course, because our teachers like us, it will. So this will factor as p minus 1 times p minus 8. Okay, and so that says, hey, actually, we have two candidates. P equals 1 and p equals 8. Okay, good. So we're ready to draw our phase diagram. And so we'll mark 1 and 8. And now we just have to figure out what's going on. Well, suppose I plug in p equals 0, right? Well, that's easy. This part will be 0, and then we have minus 4, which means that p prime is negative here. Okay, so that says we're negative, we're moving to the left. What about number between 1 and 8? Okay, we can, I don't know, 4. 4 is between 1 and 8. Sure, why not? Okay, 4 times a half is 2. 9 minus 4 is 5. 2 times 5 is 10. 10 minus 4 is 6. That's a positive value. So p prime is positive. Positive means we're increasing. We're going up. And now, finally, the 8. Okay, what happens here? Well, okay, so pick something bigger than 8. Say 9. 9 is bigger than 8. And 9 minus 9 is 0. And 0 minus 4 is negative. Okay, so p prime there is negative. Well, what does that mean? It means we're moving to the left. All right. Well, good. Well, we're almost done. We've drawn the phase diagram, and we found the critical points. Now we just have to classify. And 1 is unstable because we move away. And 8 is stable because we move towards. And there we go. There we go. There's the answer for part B. All right, good. Nice. Well, another problem down. Just 2 problems left. This test is flying by. All right, that brings us to number 5. Find the general solution to x squared y prime minus xy minus y squared equals 0. Now, it's not exactly linear first order. It's not going to be separable. It's really hard to separate. Usually when you think separable, you really want, like a bunch of stuff multiplying equals a bunch of stuff multiplying, and you can somehow separate the x and y. That's not what we have here. Not yet. And you can say, well, maybe it's exact. No, it's not exact. And so that leaves us with substitution. Now, it turns out that depending on how you look at this problem, there's 2 different ways you could approach it. Okay, so what's the first way? Well, the first way is to say, it looks a lot like x squared y prime minus xy equals y squared. And then if you covered up the y squared, say, that's linear first order. And this is y to a power, which means that this can be thought of as a Bernoulli problem. And so, okay, whoops, got to spell Bernoulli correctly. It's one of the challenges of the Bernoulli approach. All right, so with Bernoulli method, what do you do? Well, what I do, and this is because I'm an old person and I have a hard time doing math in my head, I'd imagine I'm going to remove this power and put it on the other side. So y to the minus 2 x squared y prime minus xy to the minus 1 equals 1. And the key here is that this part right here tells you the substitution to make. So for us, we would say, oh, u should be y to the minus 1. So that says u prime is minus y to the minus 2 y prime. Well, that's a lot like what you see there. Ah, okay. So we have minus x squared u prime. Now, the reason there's a minus is because we have to have a minus there. And we didn't get rid of the x squared, but the y to minus 2y prime, that's our u prime. And then we have a minus xu, because that's u, equals 1. Okay, divide through by minus x squared, because you want what's in front of the u prime to be 1. U prime plus 1 over x times u is equal to minus 1 over x squared. All right, now integrating factor. So for integrating factor, we grab what's in front of our u, and then we're going to integrate that. And we say, okay, e to the integral 1 over x dx, that's e to the log of x, that's x. Oh, that's actually pretty simple. So it says xu prime plus u should be negative 1 over x. And by design, no coincidence, this is the derivative. It turns out the derivative of x times u. And okay, so that's what we have. And now we integrate both sides. And what do we get? Well, we get that x times u is equal to minus log of x plus c. But u, remember, is y to the minus 1. So this is really x over y. Well, now you can multiply the y across, divide that across, and you get that y is equal to x over, and I'll write it as constant minus log x. Okay, because that looks better than minus log x plus constant. And there we go. Now, I said this is one way to see it. Okay, so what's the other way? Well, the other way is to say the following. You look at this and you say, what are our pieces? Well, we have an x squared, an xy, and a y squared. And these pieces all have degree 2. You might say, okay, well, why is that important? Well, the same degree means that they're homogeneous. It's a homogeneous differential equation. Okay, well, what does that mean? Well, what that says is we're going to make the following substitution. U will become y over x. Okay. Now, first off, what happens? Well, since they all have the same degree, we're going to divide through and make everything look like a y over x. So, okay, what do we have? Well, we're going to have y prime minus y over x minus y over x quantity squared equals 0. So that's if you divide through by x squared. See how everything looks like y over x. Now, remember, that's our substitution. So this says that y is equal to u times x. So y prime, well, product rule, u prime times x plus u times the root of x, which is 1. So we go through and we update. So y prime is u prime x plus u. Y over x is minus u. Y over x squared is minus u squared. And all that equals 0. All right, now we're in a great place. We notice, almost as if it had been planned, because, well, whoever wrote it probably did plan it, u prime x plus u minus u cancels, minus u squared. All right, so that gives us that u prime x, which we can write as du dx times x is equal to u squared. And now this is separable. All right, good. So what can we do? Well, we separate. So 1 over u squared du is equal to 1 over x dx. Now, the integral of 1 over u squared, because after you separate, you integrate, is minus 1 over u. And here, the integral of 1 over x is log x plus c. But wait, what's minus 1 over u? Well, since u is y over x, 1 over u is x over y. So this is minus x over y. So what we can do is we can multiply the y across, divide the log x plus c across, and we get y is equal to minus x divided by c plus log x. And there we go. Now you might say, wait, are those the same? Well, yeah, because what you can do is multiply top and bottom by minus 1, and then the c can absorb the constant. So they are the same. So we could have done this in 2 different ways. And does that make the problem harder or easier? I don't know. Is there a right way to do it? And actually the answer to that is the right way to do it is whichever way you'll make the fewest number of mistakes. And so that varies with the person, and whichever way you see first. And so don't panic if you said, I didn't see Bernoulli, or I didn't see it was homogeneous. It's okay as long as you saw something. So if you didn't see anything, it's okay to panic a little bit. But I mean, I guess the good news is we didn't take the test, so that's all right. But someday you will. And for that day, we want to be ready. So, all right, that was number 5. That means there's only one problem left. All right, let's find out what it is. And let's hope it's a good one. Our last problem. Number 6. Find the general solution. And then we have y triple prime plus 4y prime is equal to 16x plus 4e to the x. So here we see we have this right-hand side, which tells us, this is non-homogeneous. Now, when we encounter a non-homogeneous problem, we might say, well, what methods do we have? We have undetermined coefficients and variation of parameters. But do we have variation of parameters in this case? And why is the answer no? Well, we don't, because for variation of parameters, you need a very particular thing. You need to have a second order differential equation. This is the third order. So in fact, we don't have a choice. We are going to have to do undetermined coefficients. It's our only option. But you know what? That's not really a bad thing. We would have done it anyways. Because when undetermined coefficients work, it almost always 95% of the time is the preferred route to go. Okay, so, well, this will take us a moment here because there's a definite process you got to work your way through. So the first step is to say what? Well, remember, y looks like what we call yc plus yp, our homogeneous solution and our particular solution. So step 1, find the homogeneous solution. So we start with y triple prime plus 4y prime equals 0. And this becomes r cubed plus 4r equals 0, or r times r squared plus 4 equals 0, which gives us 0 and plus minus 2i as the roots. Now 0 will lead to a solution of 1. 2i and minus 2i gives you cosine of 2x and sine of 2x as your solutions. All right, so those are our parts of our homogeneous solution. So yc looks like a plus b cosine 2x plus c sine 2x. Okay, now for the non-homogeneous, we switch gears. We say, okay, let's make our first guess. And we say, well, how do we do it? Well, we look at our functions. We see x. So we're just going to say, okay, our particular solution, moving up our alphabet, will be d times x. But since this involves the power of x, we got to work our way down. So it's not just d times x. We also have to add any lower power. So like e times 1, x to the 0. Then we see e to the x. Okay, so that says we should guess something in the form f times e to the x. Okay, good. And, oh, wait, whoops. Yeah, no, we're good. So far, so good. And they say, okay, do we overlap? We do. Okay, so after our initial guess, we see overlap, so we have to modify our guess. In this case, see how we have both constants, meaning, there's a bump involved. So we're going to multiply the parts, so e will get multiplied by x, but now we say, oh, that looks like this, so we have to multiply this by x as well. We are not going to multiply this by x because that's not involved in our overlap. So it's only the parts of the same form. So this is like e to the 0x, this is e to the 1x, and 0 and 1 are not the same. Okay, so this is our real guess. Okay, so there we go. There's our differential. Well, there's what our particular solution looks like up to figuring out what d, e, and f are. But the good news is these are easy things to take derivatives of. So the first derivative, 2dx plus e plus f e to the x. The second derivative will become 2 times d. That goes away, f e to the x. And the third derivative will be f e to the x, because the constant goes away. So what do we have? We take the third derivative plus 4 times the first derivative. We should go here. Third derivative plus 4 times the first derivative. So we have f e to the x plus 4 times 2 dx plus e plus f e to the x. Well, okay, let's gather. So there's an f and 4f. Well, that makes 5f e to the x. And then we have 8dx, and we have 4e. Now, what's the key? This needs to equal 16x and 4e to the x. And we do our matching. So we get to the conclusion, well, 5 times f has to equal 4, 8 times d has to be 16, and 4 times e has to equal 0. Well, that helps us solve. E should be 0, d 2, and f is 4/5. So our particular solution is what? So it'll be d times x squared, so that's 2x squared, e times x, which is 0, and 4/5 e to the x. So what's the last thing for us to do? Well, is to combine our two parts, right? Because y is the two things added together. So our final answer is a plus b cosine 2x plus c sine of 2x plus 2x squared plus 4/5 e to the x. And there we go. Life is good. Whoop. There we go. Life is good. And we have our answer. Whew. We fit it on a page. And which isn't bad. But you know, this one definitely is the most involved, right? Because there's more steps involved. Well, that's probably why I made it the last one, to go out on a high note. Well, it was a fun test, and I hope you enjoyed it, and hope you do well in your continued studies. And we'll see you again. Bye.